somebody should do something. Ultimately, I figured out I was that somebody.
I am pleased to welcome our guest, Henrik Stiesdal, the father of modern wind power.
Floating offshore wind simply opens another world of areas that can be used for power generation for populations and for society and for industry. If we want to be resilient in a world where you cannot trust your allies and help your enemies, then the proper thing to do is to make renewable energy.
Hello and welcome to another episode of Excellence in Global Offshore Wind. I am pleased to welcome our guest, Henrik Stiesdal, the father of modern wind power. Henrik, welcome.
Thanks a lot. Thank you for having me.
Take us back to the trip to the seaside as a 12-year-old with your father, where you first got to experience the power of wind, and then fast forward to the oil crisis and the need for power on the farm. Can you walk us through how you got into wind power?
Yes, of course. I had the good luck to have a father who was very interested in science and nature and technologies. He was a teacher at a teacher's college and taught physics and chemistry. And once, when I was in my early teens or around 12, we had a stormy day, and he said, "Shouldn't we take a trip to the sea?" Here in Denmark, the North Sea lies between us and Great Britain. And when we have stormy days, you can get a quite impressive set of waves coming onto the shore, and you can get a lot of wind-blown foam and other interesting things, at least for a 12-year-old. So we drove out there and tried, as many people have tried before us and later, to lean out in the wind. It was steady enough so that you could actually lean out with your arms outstretched in a position where you would surely have fallen on your head if it had not been for the wind that came up over the dunes. And that was totally seductive. On the way back, we measured the wind speed by adjusting the speed of the car so that when you held your arm out of the window, you could feel neither a wind from the speed if you were going very fast or wind from the back when the car was going slower than the wind speed. So we could measure the wind speed in this primitive way. And that was in itself very seductive. Then we had, several years later, the first oil crisis, where the oil exporting countries, particularly the Arab countries, decided for the first time to use oil as a political weapon. Directed against countries that supported Israel in a recent war against Egypt and Syria. And we had actually quite difficult times for a period in Denmark when it was uncertain whether we could get the oil on which most of our energy supply was based, both transportation but also electricity production and heating. And we had for half a year car-free Sundays, where you could not drive on the streets unless you were the police or a doctor out doing home visitations with a patient. So that was somewhat of an awakening. We were living on an old farm. Our main building where we were living was 100 years old and not particularly well insulated. And when the oil crisis was over, with all the turbulence and the big variations in energy prices and so on, it kind of settled down to a new situation where energy cost, in round figures, 3 times as much as it had done a year before, and for a long period until then. That was not without challenges for a small, not very wealthy family on a farm, even though my parents had jobs outside the farm. And I often thought that somebody should do something. And that's, of course, so easy to say. Ultimately, I figured out I was that somebody. I did that after I had finished high school and had some time on my own before I was going to join the army. In those days, in the 1970s, and this is from 76 and onwards, we had national service, as it was called, where you had to join the army unless you were fortunate enough to draw a lottery ticket that got you off the hook. I was not that lucky. I had to join the army, which was fine. It was a great experience. But aside from that, you couldn't decide yourself when you were drafted in. And I had actually the better part of half a year until I was going to join. And there I thought, maybe this was the time to do something about this. So my father and I visited an interesting wind experiment where a set of teachers had decided on a teachers' college in the western part of the country where we have a lot of wind to build a very large wind turbine. They had suffered, like we had on the farm, due to the escalating energy prices. And they said, well, let's do something. Let's do something radical. Let's transfer to wind power as our fundamental source of energy. Let's get a big wind turbine. And after a little shopping around, they discovered there is no big wind turbine to be had. But what they then did was that they took a very, what shall we say, engaging, in my view, approach where they say, okay, if we can't go out and buy it, let's build one ourselves. All right, we don't know if we can build it. But a bit like the star of one of the Scandinavian children's books on Pippi Longstocking, Pippi herself once speaks with her friends and says, I think I'm going to play the piano. And then her sensible friend says, but Pippi, can you play the piano? And then she says, I've never tried to. There's no reason to believe I shouldn't be able to play the piano. These people had never tried to build a big wind turbine, but they went about it in pretty much the same way. They, of course, got a lot of assistance from technical people in Denmark because they were very good at engaging universities and research institutions and so on to have them help with fundamental design elements and so on. But when it came to the practical execution, they built the blades, they built the tower, they assembled the machinery and so on. And that was extremely engaging to visit them, which I did around Christmas 76. So as you and I sit here and talk about 49 years ago and looked at what they were doing and thought, of course I shouldn't be building the biggest turbine in the world as they were. I should be building something much smaller, enough to power a farm reasonably. But the whole approach and attitude was just charming and engaging. So we started with a little handheld rotor, about 1 meter diameter, that we mounted on actually a piece of water pipe that you could hold in your hand and kind of get a feel for it. And that was super fun, and it worked fantastic, and it was super dangerous because it span with 300 or 400 miles per hour just in front of your nose. But it was so engaging. Then I built a 3-meter rotor, 10 feet, that I mounted on a sort of miniature tower on the farm wagon. I didn't have time or money, or shall we say, I didn't feel I was where it made sense to build it as a genuine turbine that would stand out there all day and all night. But I thought I could run it out in the field when there was a good wind and measure how much could it actually produce. So we built a small anemometer, a device to measure the wind speed, and we made arrangements so we could measure the electrical power generated with this 3-meter rotor. And of course, I had some theoretical understanding of what went on, and I knew from literature that I had been pursuing for after I had been to this visit to the Teachers College, what one might be able to expect. But still was something entirely different to actually do it and see that on a windy day we could produce all the power that was used on the farm by this little rotor. And then, of course, the path was set. I joined the army, but fortunately you also often got the weekends off, and so I could work with this while I was doing my tour and I could also work in vacation periods and so on. So over the next 1.5 years, I built a 10-meter rotor with 15 kilowatt power. And that was the real thing. It came up in the spring of 78 and ran for many years on the farm, 15 years I think it was, and produced the power that we needed and much more we could sell to the public grid. And that was of course hugely satisfying, but in a way also a sort of single track, egoistical, this is what we do for the family thing. But in the course of this, developing the technology, figuring out how to do it, speaking with people, so on, I discovered that there was actually in those days a whole pioneering community in Denmark. I think at one point there may have been 25 or more people building their own wind turbines, or trying at least, many succeeding, many also failing. But there was this spirit of can-do that was very attractive to become a member of. And during the course of that, I got to know a machinist in a nearby small town who had built a small wind turbine for himself and was considering building a bigger machine, but he did not have the schooling background for actually doing such a thing. He was a super good craftsman, but he was not a bookish type. At that time in early 1978, I had some elements of my turbine that I could not myself machine. I had an old lathe on which I could turn things. I could do a shaft or things like that. I could weld, I could drill, but I couldn't do what you call milling, which is what you need to do when you want to make shapes that are not cylindrical. And he could do that. He had a milling machine. So we made an agreement that I should help him design a wind turbine, and he would then do the machining for me. So I designed one for him. It worked very nicely. And then, of course, we all got a little fired up about it, and I designed a bigger machine for him that he then could go out and sell to people. He sold a few of those machines in spring of 1979, and they worked like sewing machines. It just was. It came easy. When I sometimes think of it, I think we had fantastic luck in not, I would almost say, getting killed, or at least failing miserably during this period. And then in the summer of 79, he came to me and said, we have this thing. It has huge perspectives. Just build a factory. Then we'll make a big impact. And I thought, this won't work. He has no clue about money. I have no clue about money. I have some self-taught technical insights, but not nearly enough to run a manufacturing facility or anything like that. And by the way, maybe I should also have an education. Maybe I should go to university, or rather, I knew I was going to university, and then I couldn't engage in a thing like this. So what we ended up doing was looking around for somebody who would produce our machine on a license, who had an interest in wind power, but who might not yet have the technology that we could take. So, and then it turned out purely by coincidence that we discovered that a company not so far away, 25 kilometers or 30 or so, called Vestas, was somewhat interested in wind. They had acquired a license for another type of turbine that we knew would never work. And then so maybe there could be an opening. So I gave them a call. This was long before emails or anything like that. I gave them a call, and then I somewhat cheekily said, I know you are interested in wind. Shouldn't you get a proper wind turbine? And they did not get offended, came out and saw what we were doing. And we ended up making a deal where they would produce our design, not for us. They would simply take over the technology. We would get a certain payment, a small payment per turbine, And in that way, both parties would be good. They would get a technology much faster than if they should have developed it themselves. We would get some economic reward, but in a way, much more importantly, see our ideas materialize in significant volumes in this way. So that's how it all started. That's how Vestas, which is now the biggest Western world company in wind power, got started. And that's how almost you could say that the Danish wind industry got started. Sometimes I'm called, as you started by saying, the father of modern wind power. That's not true at all. There were many, many players in the field. I had the good luck to, be part of some things that move things forward. I had the good luck to actually engage with somebody, Vestas, who had the competences and the drive to make this big and so on. But there were 50, 100 or more people involved in getting modern wind power off the ground, including even before us, people in the US. But you can say that the design we ultimately licensed to Vestas had all the elements that came to describe modern Danish wind power. And that way, I was lucky to be very much at the right place at the right time.
What a fascinating story, Henrik. And you are, obviously very humble. What was it about the Danish concept, the three blades? What do you think, what was the unique piece that made it so much more successful than the other designs?
When you say the other designs, it can actually, you could split it in two dimensions, I would say. You could split it in large and small, and you could split it in, roughly speaking, US and Danish. If you take the large and small, in parallel to this development of the industry, there were many research projects going on that were more at a government level. That happened in Sweden, in Denmark, in Germany, in Spain, in Italy. It also happened large scale in the US, headed by NASA. A common feature of these large scale turbines were that they were, by the standards of the day, very large. Generally significantly larger than this largest turbine that they had built at the Teachers College, and applying thinking that was driven by either big corporations or by consortia of research institutions and companies and so on. And what they all shared was that they did not have a big traditional link back to production industry. And in actual fact, it is kind of difficult to make big turbines work technically and commercially. It is typically much more difficult than was envisaged at the time. So most of these national projects ran into difficulties. They would install turbines that would fail or would not structurally fail, but turn out to have flaws that were not feasible in the long run, or would be very noisy in places where they could not allow themselves to be noisy, and so on. A lot of information was gathered, but no industrial product ever came out of these big scale projects. Then there was the other thing, there was the small turbines, and they were developed largely in the US and in Denmark. And there the approach was different in the sense that the Danish development happened at a much less informed level. We simply had much less clue about aerodynamics and structures and so on. But to compensate for that, we had the traditional, low-key or practical approach to when you do things you are not fully sure of what you're doing, in that you just add steel until you feel that now you're really on the safe side. So the Danish turbines came out of an agricultural machinery culture, and the American turbines came out of aerospace, where weight saving and optimization were driving factors because they were always driving factors in rotorcraft and stationary wing aircraft. And there, the American approach was hit very hard by the fact that working at much lower speeds for the moving parts, the blades, than what is customary in the aviation industry, particularly in rotorcraft, but also in propeller-driven aircraft, meant that turbulence effects were much more important than they were in aviation or in aerospace. In Denmark, we did not have any big clue about turbulence, but we just ended up building machines that were strong enough to take anything that was thrown at them. When it came to the three-bladed, many of the American turbines were two-bladed, and there is this distinction between one or two blades. You can make a one-bladed turbine by just having a counterweight and then one blade, or you can make a two-bladed turbine. They are not what we call dynamically stable, so they have a different response whether the blades are in the vertical position or in the horizontal position. When you have three or more blades, your rotor is dynamically stable. Its physical characteristics don't really depend on the direction of that the rotor blades are oriented during the revolution of the rotor. And we knew that by reading literature and also with my own handheld rotor, which was a two-bladed, I could feel some of the challenges there would be with the two-bladed machine. And therefore we selected the three-bladed concept. There were also two-bladed made in Denmark. They also suffered. So the three-bladed concept turned out to be really the most practical way because it suited our competence level, which was not very high. And in that way, the heavy Danish machines came through the formative years that were not always easy in California during the early and mid-80s, where in some places we had very high turbulence without basically any problems because they were just over-designed so much that it didn't matter we fully understood what was going on. Whereas most of the American machines were designed much closer to the limit, and then when exposed to difficult conditions, they didn't work. They couldn't last. They would throw off the blades or fail in whichever way. So you can say that where we came from was, what would you call it? It's almost a bumpkin approach. The farm boy who doesn't really fully understand what he is doing, but then he adds some more steel. What the heck, 5 millimeters more doesn't hurt. And then it was just big enough.
It's interesting. The other piece I hear is, your entrepreneurial spirit and your why. The reason was very strong. You were doing it for the family farm. It wasn't a research project that was theoretical or a consortia that was looking to optimize. And so it's very interesting. You were looking to solve a very real problem that was very close to you. And that why is strong. And I think, as entrepreneurs, that is a critical element. So, kudos. And the can-do spirit that you mentioned is also, I think, a big part of that. Interesting. So then, let's fast forward. So Vestas licensed the technology and the design, and then they start producing and fast forward, you end up joining Vestas.
My license deal with Vestas helped me get through the first half of my study time without having to work in parallel to the studies. Here in Denmark, we have free tuition. So there's no tuition fee or anything when you go to university, but you still have to take care of yourself. Nowadays, people get also subsidies to help them do that. It was not so easy in those days. There were small subsidies. I always ended up just working and not getting any money from anybody. But after the first 4 years, the license agreement basically expired. And then we made an arrangement where I could work at Vestas 1 day a week while I was studying, and I could also do homework. So I was responsible for the design of the next generation turbine that became a lot larger. What they bought from us originally was a 30 kilowatt machine, 10 meters diameter. Vestas on their own developed that up into a, roughly speaking, 100 kilowatt machine. And when I was then engaged by Vestas, we developed a 200 kilowatt machine, so a significantly larger product. And I worked there and had great pleasure of that and got to enjoy very much the working life in a company, which is different from how it had been when you were a pioneer and was on your own, or maybe had a pal like I had in my friend Carl Erik, who was the machinist. And they were also very different from university, in that in university, ultimately, you are working for your own education. If you work in a company, you work in a team, and your shared goal is the progression of the company, the progression of the impact in the world. And you kind of work for each other, so to speak. And I really enjoyed that. Vestas then got into some troubles over the California market that collapsed at the end of 86. So I ended up joining another Danish company, Bonus Energy, in the early 87, and then stayed there for the next 27 years until I retired at the end of 2014. I very quickly became the technical manager of Bonus, and I stayed in that role until we sold the company to Siemens in 2004. And Siemens really took this company forward and expanded it tremendously. So I spent another 10 years as the chief technology officer of Siemens Wind Power. And it was really, fantastic in the way that you got to have impact. So when I joined the company, we were 80 people in Bonus Energy in 1987. We sold the company to Siemens in 2004, and by that time we were 801 persons exactly. And when I retired 10 years later, we were 13,400 people. So that was really fantastic, and we made every year turbines with a capacity that was much bigger than what would be needed in Denmark and so on. We had, when I retired a long time ago, passed the threshold where our wind turbines produced more electricity than was used in Denmark, even though they were not, of course, all of them in Denmark. They were all over the world, but we had this strong feeling that we really made a difference, and that was very, very interesting, and it was really a very good time.
Very interesting. And Henrik, I mean, the power of impact, you touched on a couple of times. I also think that's a really key ingredient to success as an entrepreneur. It's you're making an impact on something bigger than you. It's a mission that the company and everyone's working towards, and really drives that. I'm curious to hear your thoughts on how wind, the wind turbine industry has evolved. And specifically, I want to touch on the size of the turbines now, especially offshore, and some of the challenges that we're seeing in the industry now, especially around CapEx, inflation, supply chain. Where do you see the industry today? And then I want to go into kind of the future as we'll talk about floating as well. But tell me, where do you think the turbines have grown to a size that is unsustainable, or how do you think about the path today?
Yeah, that's a very good question. Turbines have, of course, grown tremendously. Our own first one was 15 kilowatts. The one I designed for my friend that he built at his own facility was 22 kilowatts. The one I designed for him to sell was 30 kilowatts. That's what Vestas bought. Very soon they were 55 kilowatts. And then on, they kept on growing. And for many, many years, they grew exponentially. So they grew with a doubling time of 4 years. So when 4 years had passed, the turbines were twice as big in rating. And that went on for a very long time until it started waning off but we are still growing. And I have made the blunder of making predictions about how big they would be. So in 1985, I made a strong statement at an international conference that they would never be bigger than 250 kilowatts if they were to be economical. And I think it's okay to make a mistake, but then I repeated it at another conference in 90 and said, okay, I was wrong first time, but now I knew for sure that they would never be bigger than 500 kilowatts. And now the big offshore turbines are 15,000 kilowatts. So it's 30 times bigger than my prediction. So I learned the lessons and I don't make any predictions anymore. In a way, with 3 different perspectives. Particularly offshore, it was always good to get bigger. Because with the bigger turbines, you have less numbers of foundations, less numbers of cables to install, less numbers of installation processes with big vessels and so on. And that has always been the driving factor that bigger is better. When I then look at other industries, that same thing has happened in other industries. And my 2 pet examples are crude oil ships, so oil tankers, and aircraft, commercial aircraft. From 1945 and until about 1985, oil tankers grew exponentially in what is their measure, which is tons of deadweight or tons of carrying capacity or whatever. It's not so important. From about 15,000 tons after the Second World War to about 500,000 tons. And then they stopped. Bam! Suddenly they didn't get any bigger. And now they are rather smaller. The biggest vessels that are built are about 400,000 tons or less. So they reached a peak, stayed there for some time, and then declined. And the reason for that was practical, that a ship of 500,000 tons is kind of, it's difficult. If you go full speed ahead and something happens ahead of you, it'll take you half an hour to stop. And the ports that can take these big ships are few and far between and so on. It was just not good, even though on paper, the bigger is always better. On commercial aircraft, they grew. If you take the all-metal aircraft and leave out the wood and canvas planes of earlier, they started making all-metal aircraft around 1935. So from 1935 to 1970, aircraft also grew exponentially. So after so many years, they were twice as big in their yardstick, which is maximum takeoff weight. Until 1970 or 71, thereabouts, when we had the Boeing 747. And that was then the biggest aircraft for decades to come. There were bigger versions of the 747, but for all practical purpose, it was the same. We had one that was bigger. That was the Airbus A380. It was rather bigger than the 747. But it was too big. So the Airbus A380, as far as I know, never earned the money that it had cost to develop it for Airbus. And after 15 or 20 years, they stopped producing it. And now they have also stopped at Boeing to produce the 747. And the biggest aircraft you can buy now are rather smaller than the 747. So just like the oil tankers, they grew exponentially, hit a ceiling, stayed there for a little while or for some decades, and then dropped down again. And wind turbines are growing exponentially. And I have some concerns that they would have the same trajectory, that at some point they will become too large, and then we will have to reduce again. Then there's an extra element, and that is the power of industrialization. Things get cheaper if you make many of them. We know that from the auto industry. We know that from solar panels. We know that also from wind turbines, that the more you produce of a certain model, the less it costs. If we keep on making bigger and bigger turbines, we simply don't get enough numbers on those that we produce for a period, and then leave behind for another day and for another bigger thing. And there I'm concerned that the risks involved with the very big turbines and the lack of volume in numbers of machines might be an issue that could come as an unpleasant surprise in offshore wind. But I cannot, and I don't think anybody can say where that limit is. I'm totally convinced that there is a limit. I don't know exactly where it is. But I would in many ways prefer that we stayed within somewhere around 300 meters maximum height to the tip of the blade, because then we could get the volumes up and the cost down.
Those are two great analogies with the oil tankers and the aircrafts. The question is, have we arrived at that, at that maximum, or are we ready to pull back a bit? Of course, we hear the Chinese, working on 18 and 20 and 25 and sometimes even bigger, based on some of the things we're hearing. But it'll be interesting to see, because I agree with you. I think standardization and industrialization, to take advantage of bringing the cost down is a counter to scale, economies of scale.
And there you can say, if we were to do something, what could we do? We could impose regulations. We could say, don't get above 1,000 feet, 304 meters. Then a lot of people will say, that will stop innovation. That will blah, blah, blah. But we have other industries where such maximum limits do exist, like, for instance, on trucks, where there's, in most countries, is a maximum weight. And it's not so that truck innovation stopped. Trucks are now much better and give us much more value for money than 30 years ago. So they have worked within a limit, and they keep on innovating and keep giving us cheaper and cheaper transportation. If fuel prices had been constant, we would get cheaper and cheaper transportation because of innovation. I think that the truck industry benefits tremendously from having standard products. The Chinese big players are now in the range of 20-odd megawatts, 21, 22, some are even bigger. The Western player with the base machine is Siemens. They have a 21.5, I think it is. And the mainstream today from Vestas and Siemens and GE is otherwise 15 megawatts. Siemens has recently stated that they expect to make a decision about going into mass production, but it sounds as if they have not yet made that decision regarding the big machine. And I would expect that they might well have the same considerations as what we are discussing here, whether it would be better to maximize the benefits of volume or whether it is necessary to go to the bigger machine. And it'll be interesting to see where they land.
Yeah, absolutely. And similar to the truck example, the enabling infrastructure, the roads and all the other elements. And then if you apply that to the wind industry, whether it's the offshore installation vessels or, onshore cranes and so on, it allows, the enabling infrastructure also to standardize and get economies of scale, cost reductions. So it'll be interesting to see.
Yeah, take a simple thing like transportation brackets and equipment to allow movement of the machinery in the factory. Before you have spent $500 million on that sort of equipment. That doesn't really create value. They're just enabling things that cost a fortune and might not work on the next bigger machine. So things like that, I think, are really necessary to take into account when I do my own optimization calculations. And they are, of course, affected by uncertainty like anything else. I do get an improvement of project economy out to somewhere in the range of 15 to 20 megawatts. Then project economy gets worse again. I might be wrong. It might be that it gets marginally better. But for all practical purposes, the curve is horizontal from 15 to 20 megawatts. Well, if it is horizontal, and with 15, you get 50% more units than if you produced at 22.5 megawatts, why would you want to do that? So it'll be interesting to see how it develops.
We'll follow up in a few years and see.
Yes.
What about, so maybe just, dig in a bit deeper on where we are today, specifically with offshore wind. And we've seen, as you know, I'm based in Canada today. You're in Denmark. Our neighbors to the south, there's some regulatory and some changes coming from the administration that say, look, we don't want offshore wind. I don't know if they prefer not to look at them, or, what do you think? Does offshore wind continue to have a role in the energy transition globally? And do you think this where we are today, will we get over this bump, and how long will that take?
Yeah, I'm totally confident that it will keep on playing a bigger and bigger role. If you look at Europe, where I'm sitting today, in round figures, my expectation is that as we go forward, the energy supply in Europe, when it comes to electricity, and a very big part of our energy supply will become electrified, I expect that it'll be split into 4 quarters, 25% offshore wind, 25% onshore wind, 25% solar, 25% the rest being geothermal, nuclear, some biofuels, other things. The big upside of offshore wind is that the social acceptance, at least in Europe, so easy. Most of the projects you cannot see from the shore. You have a cable coming in. Through that comes what you could almost call power from an invisible source or something like that. Huge amounts of power from something if you don't know what it is, you don't know where it comes from. It has no visual impact in the landscape and so on. So there I'm totally convinced. But it's clear that we have some effects that are combining to make the industry more shaky than it, in my view, should have been. One thing is, of course, the Trump administration's opposition to offshore wind, which is, I don't see any rational argument for, but which is more, in my view, emotionally anchored. But when you look at Europe, we have a number of factors that play a negative role. First of all, of course, we have had inflation. And then we have had a sort of shared feeling among the big players that for many years, they ended up not making the money that they should on offshore wind because they were always competing against each other and prices got lower and lower. And it seems like a thing where you had difficulties breaking even. I think that they have now realized that they are in a position where they can up the prices quite significantly to make it a nicely profitable business because there are not that many players. They don't have any cartels or any internal agreements and so on. They are not allowed to do that, and they for sure don't have that. I think there's a shared feeling that if they are to stay in offshore wind, they need to have good, solid, profit-making businesses. And that's fair enough. But then we have regulatory and grid-related issues that play a negative role. When I look at the most trivial analogy in the world is the chain. You have a chain of things that need to happen in order for an offshore project to be made. And you could say it can be done. You can phrase it in any kind of ways, but you could say you need a developer who wants it to happen. He needs to be able to get the technology that works. He then needs to get his planning permission. He needs to be able to be able to deliver the goods. He needs to be able to get rid of his product, electricity. He needs to have social acceptance. He needs other things. And he needs to get financing and so on. And here the thing is, many of the chain links are there and are strong and solid and good. We have no end of developers who want to do projects. All the technologies work. Offshore wind just works. High reliability, high productivity, what have you. There's no end of money. You can get anything financed as long as you have a good business case. The Western world is brimming with money. When you're offshore, social acceptance is not a big deal. That's not the problem. But there are 3 major bottlenecks that are not trivial. The first one is getting your planning permission is an extremely lengthy process, much worse than it should be. When I was involved in the first offshore wind project in the world back in 1991, we built 11 turbines with a total rating of 5 megawatts, and as the very first project. When our client decided that they wanted to do this project, they submitted their planning application and they had the building permit within 1 year. Even though it was the first in the world and there were many, many considerations nobody had ever done before. Now it takes anywhere between 4 and 7 years. Then when it comes to the grid, here in Europe, the grid operators, we call them the system operators or the transmission system operators, TSOs, they are not rewarded for planning ahead. So they are not encouraged to build a grid that can take next year's delivery of electricity. And that means that when you want to develop a project, you look into a planning process that's really lengthy. And if you are successful, you might not be able to get rid of your power. And that is really a clamp on the industry. The third bottleneck is the supply chain. Okay, if you get your planning permission and if you get your grid connection, can you then get the turbines, the foundations, get the ships and so on? And at the moment, the simple answer is no, they have not ramped up so that they can really follow the demand if the first 2 bottlenecks were removed. But fortunately, they don't need any special arrangements to be able to do that, because once you have a demand, for sure the supply will come. They will go out and invest in factories. As soon as their customers say, I'll buy from you, I'll buy actually several projects over the next 10 years, please make sure you can deliver. Then they will build their factories. But if somebody comes and says, I have this project, maybe I get a permission. And if I get that, I might be lucky enough to get rid of the power. And then I might come back to you. That is not something you can build an investable factory on. That just doesn't work. So what we are missing here in Europe at the moment is a good, strong setup that will cut the planning commission time to 2 years maximum, and that will incentivize the system operators to build the grid so that you can get rid of the power once the turbines are in place. Then industry will come, then we get volume, then we get cost reductions. That is the positive spiral. And that is eminently doable. It's not rocket science. And the fundamental, shall we say, statement about it is that we need to create a demand. Once we create a demand, supply will follow. But the demand is not created if you don't have the planning system in place and if you don't have the off-take, as we call it, system in place where somebody will use your electricity.
Yeah, absolutely. The planning, shrinking up that time to get your planning is really critical. And like you said, the grid it's a bottleneck, not just in Europe, but globally. We don't see that planning ahead. Back to your trucking analogy, it's like, we're not building the roads until, we get more trucks, and now we have to wait for the roads to be built before we can use the trucks, right?
Yeah, exactly.
So I want to go back, on a quick question, and then I want to talk about floating offshore wind. But you talked about the profitability of the manufacturer, the turbine suppliers, and there's less competition, so there's opportunity to really increase margins. Do you see the Chinese OEMs successfully being able to enter the Western, including European markets? I mean, we see they're definitely pushing hard to do that. What do you think?
It is a good question. You can say, you could, in a way, you could split that question as, would it be a good thing? And if it was a good thing, would it then happen? And seen from my perspective, it would be a good thing, subject to the condition that the machines are made in the Western world. The Chinese suppliers good at making decisions. They are entrepreneurial. They are forward-moving. And if they do like the Chinese company Mingyang is planning to do, build a factory in Great Britain, build their blades there, assemble them themselves by Western towers, then they might end up having more Western world content than many of the Western suppliers who get sometimes the majority of their components from China. Is it then bad? What is the only bad thing is that then the owner is Chinese. But I mean, a Chinese company could buy all the Vestas shares. Would Vestas then become a bad persona non grata? Of course not. So why is then a Chinese company who is building their machines in Europe a bad thing? Will it then happen? That's a good question, because it's very emotionally charged. And there's a feeling in Europe that we lost the solar industry. We lost the battery industry. I'm now also going to lose the wind industry. And there's also a sort of general reservation in relation to Chinese products and this search for dominance that we very often hear about when we orient ourselves against Chinese manufacturing. I think that if there's a level playing field, if the Chinese company is not receiving undue state financing or in other ways kind of have unfairly beneficial conditions, then I would welcome this, and I hope that the governments, in the first case the UK government, will do the same. But we'll see about that.
Shift into floating. So you've recently announced a very interesting alignment partnership with CIP, Copenhagen Infrastructure Partners, and some of the folks that we know there. Tell me a bit about your focus today and your why, your mission, as it relates to floating offshore wind. What is your view on the direction of that industry?
In a way, you could start by simply asking the question, why would you worry about floating offshore wind? Why not just stick to what we have known now for 35 years with bottom-fixed offshore wind? It's a big success. What is this all about? And what is it about is that bottom-fixed offshore wind, or offshore wind, the foundation reaches from the seabed up to the turbine, can only economically be built up to a water depth of about 60 to 70 meters. When you get beyond that depth, you can still do it technically, but it becomes too costly. Now, the consequence of that is that traditional offshore wind can be built in large areas around northwestern Europe. It can be built on the US East Coast. It can be built on the Chinese coast. It can be built to some extent in some parts of Korea, Taiwan, Japan, Australia. End of story. Cannot be built on the west coast of the US. It cannot be built around most of South America. Cannot be built around most of Asia or Africa. It cannot be built in most parts of Australia or elsewhere. Offshore wind today could commercially supply an amount of electricity corresponding to what the whole world uses today. The whole world uses 30,000 terawatt hours per year. Denmark uses 36 terawatt hours. So the whole world uses a bit less than 1,000 times my little country. Bottom-fixed offshore wind can supply 30,000 terawatt hours with commercial projects. But in reality, that is not going to happen anywhere near that. Of course, also because there are other sources of electricity, but also because it's so unevenly distributed. Europe could not supply 10 times its own consumption to other countries that are not in Europe. That just won't happen. If you could make the wind turbines float, you could supply almost all countries that have a coastline. And the commercially available resources grows by a factor of 10. Do we need 10 times the electric power we have today? Of course not. But we need more than what we have today because we are going to electrify society, get rid of fossil fuels. And therefore we need 2 or 3 times as much electricity as today. And that is a good thing to be able to do that in more than 2 handfuls of countries. And with floating offshore wind, as I say, you can do supply of electricity to almost any country that has a coastline. The prerequisite of that is to do it so that it is affordable for people, for society, for industry. Most of the floating offshore projects that we look at today are not affordable, primarily because the machinery and the mooring systems and so on are still made using technologies from the oil and gas industry. And in oil and gas, the investment is not a very big part of the cost of the oil product. The offshore oil and gas industry has never learned to be really competitive. The wind industry is really competitive. The solar industry is, but the oil and gas industry is not. And therefore, we need to get over to use technologies that are similar to what we do in the wind industry and in the solar industry. And what we have been working with, and are working with in our little company, is to simply piggyback on existing industries in wind power, mainly the tower industry. So we are building foundations, floating foundations that are made of components that are not turbine towers, but are quite similar to turbine towers, and therefore can be made in the same factory environments as turbine towers. And turbine towers is a special thing in the world. More than 250,000 tower sections are made every year. And the result of that is that a wind turbine tower is the cheapest large steel structure you can buy anywhere in the world. It has, at the same time, the best welding quality and the best surface protection that is available, and yet it is cheaper per kilo than any bridge or ship or airport building or big stadium or whatever you'd want to build from steel, because it's made in repetitive, semi-automated processes. And what we are pursuing in our company is to do floating structures that are made using the same philosophy and using the same factories that build the wind turbine towers. And that way we are confident that we can get the cost down to the same level as bottom-fixed offshore wind. Floating wind has advantages that help reduce the cost. They have bigger foundations than bottom-fixed because they need to float and can't just rest on the seabed. They also need a mooring system that keeps them in place, typically with 3 strong wires down to anchors in 3 directions, so you can't float away in any direction. But they have the big advantage that you can install the turbine on the foundation in the port. And then you just need relatively small vessels to get that out to the location offshore where you hook it up to the mooring system. And then you avoid the very expensive big installation vessels and can use just land-based cranes to install your turbine. So all in all, floating offshore wind simply opens another world of areas that can be used for power generation for populations and for society and for industry than if we were limited to just the bottom-fixed foundations.
It is fascinating, and those elements definitely make sense. And you know, I guess the question is, how long do you think it would take before we start seeing, commercial floating offshore wind projects in scale, around the world?
The project that you referred to in your previous question about our relationship with CIP deals with a 100 megawatt project in Scotland. And that is, by today's standards, a small offshore project. Big offshore projects are in the 1 gigawatt, 1,000 megawatts or more scale. We will see hundreds of megawatts, half gigawatt scale in the early 2030s. But it will not be until we are 10 years ahead they will see really big volumes. It does take 10 years to get there. That's just the rule of the game. But if we do it prudently, if we rely on known industries that already now produce low-cost products, then we can accelerate faster than if we have to do everything by hand, which is unfortunately the rule of the game today. Most of the floating offshore foundations are welded by hand. And that's just not realistic. We don't have the welders in the world that can do that in the necessary volume. We need to get to industrial methods in order to make this happen.
You touched on the need for power and with AI and hyperscalers and data centers, in addition to electrification, space heating, all the things that we've already seen demand from. There's no questions that the fundamentals are strong. There's a need for more clean electricity at that. There are, nuclear has become a much stronger conversation. There are discussions around gas and other fossil fuels coming back. Where do you think the cost competitiveness and the real ability to get scale, will be with offshore wind?
As it is now, offshore wind is, of course, still a lot cheaper than doing any fossil combustion if you take notice of your carbon emissions and compensate for that either by paying other people to clean up the atmosphere or by having a carbon capture on your smokestack. When it comes to nuclear, modern-day nuclear projects in Europe are much more expensive than offshore wind, including floating offshore wind. And I don't see any possibility that they would come down and match the cost level of renewables. So I think that here in Europe, there are other elements. What we are speaking about here, you could essentially group under affordability. But what is extremely important in Europe at the moment, it may not be the same in Canada, but it certainly is in Europe, is energy independence. We rely to a large extent on imported energy sources, oil, gas, nuclear fuels. We import 95% of our oil, 88% of our gas, 95% of our nuclear fuels. We, by the way, import the nuclear fuels from Russia. We import absolutely 0.0 of our renewable energy because it's all homemade. If we want to be resilient in a world where you cannot trust your allies and help your enemies, then the proper thing to do is to make renewable energy, because then you're not depending on anybody. And if you look at China, they are pursuing an electrification project that is very, very impressive. They are much more electrified than they were 10 years ago. They are actually much more electrified than Europe or the US or Canada. That is because they're building out renewables at a huge rate. And I'm not privy to what considerations the Chinese may have, but I'm sure it plays a role that by using their homemade electricity, they also become less dependent on imports. Because China is not endowed with natural resources in the same way as US or Russia are. And there it's clear that from a purely logical, a purely commercial point of view, one needs to follow their guidance and electrify and base it on homegrown electricity. And that you don't get with fossils, you don't get that with nuclear.
The CIP partnership, tell us a bit more about, your vision for that and the focus on the 100 megawatt project and what we see moving forward.
The CIP is a major international developer of offshore projects, as I'm sure you know. And they also have a large portfolio of floating projects in the pipeline. And therefore, for all the good reasons in the world, it's very attractive for us to engage with CIP. And we are extremely happy that they have announced their selection of us to be the technology supplier for the first large project that they hope to build, which will be in Scotland. It's all subject to the present so-called AR7 round in Britain, where they have bid to receive a support per kilowatt hour for what power is produced from the floating offshore wind. We, of course, cross our fingers that they will get the subsidy that they are after, and we really hope that we can get this flagship project off the ground. It's in a rather complex location north of Scotland, complex in the sense that it is relatively severe mid-ocean conditions, high winds and high waves. And that, of course, means that it's not just something you do from one day to the next. On the other hand, from our side, being the technology developer, we really welcome the opportunity to demonstrate that floating offshore wind can also work in the harshest conditions out there. They have 15-meter significant wave height, which means that the biggest waves ever will get to a height of maybe 27, 28 meters. So it is, for the equipment supplier, an interesting place to be. But we really look forward and cross our fingers and touch wood and whatever else is available to us as decision-affecting methodologies to make this project happen.
That's excellent. Of course, you have the high wind experience to leverage and the success there of the project in Norway.
You can say that, just to make the terminology clear, I was at Siemens and was responsible for the adjustments of a 2.3 megawatt turbine that came up on the Hywind demo. Hywind was the name selected for the first offshore floating project ever that was built in 2009 by the big Norwegian oil company Statoil, now Equinor. We are, in relation to the CIP project, relying more on our experiences with our own floater, the Tetraspar demo, that came out a little over 4 years ago and has been producing power west of Norway, not very far from Hywind, but with a bigger turbine for the last 4 years. We have a 3.6 megawatt turbine that has been running very, very well. And we have a very high energy production out there. So if somebody should ask, does the fact that it's floating affect negatively generation capabilities of your product? The brutal answer is not at all. We have a very high, much higher than 50% capacity factor out on the project.
Yeah, and I've heard that you've reached close to 60 or 63% capacity factors in certain moments.
Yeah, but other projects also do that from time to time. For us, the most important figure is the 4-year average, where we are well above what we predicted.
I always like to end the discussion with a question of looking back, and we talked about the story when you were 12 years old with your son, with your father going to the seaside. If you had any advice for your 20-year-old self, or maybe others, younger folks looking at this industry, what words of advice would you give them?
Yeah, that's actually a good question, because in a way you can't really, I'm 68, it's not that easy to put yourself back in those days. I think I was fortunate enough to have been brought up in a way where when problems were encountered, you looked at them and you said, okay, how do we overcome this? And that's in a way how I have run my whole business life. And I think that is a good thing. In Denmark, we are also blessed with a educational system and a hierarchical structure in our companies that is very egalitarian. So that we have a healthy disrespect for authority, to be quite frank. And I think that's good for independent thinking. But most of all, I think that 20-year-olds should pursue the ambitions of their life. It might change over time. It might but not be that the 20-year-old ambitions and expectations are the same when you reach 30 or whatever. But that you do it, and hopefully, if it feels relevant for you, in one of the fields that would help support the energy transition away from climate-destroying energy sources like fossil fuels and over into climate improving, or at least not worsening, renewable energies and technologies to take CO2 out of the atmosphere. Climate change is, no matter what we might think of the world situation today and the depressions we get about wars in Ukraine and in Gaza and elsewhere in the world, climate change remains the single biggest problem that we will be facing and the 20-year-olds will be facing. And there I can say that to the extent you can, being in wind power and most likely also in other renewables industries, my own experience is mostly in wind, but I also work with hydrogen and green fuels and so on, is the most fascinating, exciting place you can be. First of all, because there are still many new technology elements to explore. And secondly, because you have the possibility to really influence events in the world and to have impact, as we spoke about earlier in the program. And there my advice to young people, besides these sort of more personal things, don't have too much belief in the authority. Take a good entrepreneurial approach, pursue your goals and have fun in the process. It is also that the renewable industry is a fantastic place to be.
On that note, I think that's a great note to end on. Pursue your passions, be entrepreneurial and have fun.
Yes.
Henrik, it's been a pleasure. Thank you.
Very good. Thanks a lot. Pleasure to be here. Thank you.